Okay, so this is part C of chapter 24. This is going to be the pH balance. So acid-base balance is another term. Some of these are going to be review. Some of them we're going to expand on what we did the first time. So pH is the concentration of hydrogen ions in solution. Mathematically, it's the negative log of the hydrogen ion concentration, also minus log hydrogen ions. Normal blood pH is 7.35 to 7.45. In various parts of the body, it can be higher or lower, but again, that's the normal blood pH. And we had that in chapter 18, so that shouldn't be anything new. Again, we had the ionization of water in chapter 2. So hydrogen, H2O, water, will dissociate into hydrogen ions and hydroxide ions. So with pH, we are focusing on the hydrogen ions. Again, lowercase p, uppercase h. So there's also a pOH scale. But we don't get into that. If you take a full chemistry class, they will get into that. So with pH, we're focusing on hydrogen ion concentration. Mathematically altered scale. Okay, so you have this version of a pH scale, which has the whole scale from 0 to 14, and it gives you some various components, various compounds and substances, and where they fall on the pH scale. So this is another version of the pH scale. It also has various components. We describe the pH scale as from 0 to 14. At pH 7, you have the same amounts of hydrogen ions and hydroxyl ion concentrations. That's what the brackets stand for. So with pH values, they're mathematically altered. Thankfully, it's a log 10 rather than something else. So basically, we're moving the decimal point. At pH 0, you have a 1 molar solution of hydrogen ions. That's the most amount of hydrogen ions. At pH 1, we have moved the decimal point over a 0.1 molar solution, which is 1 times 10 to the negative 1. A pH value of 2. We move it over again. I guess it should go this way. 1 times 10 to the negative 2, and so forth. So a smaller pH value means that you have more hydrogen ions. So more hydrogen ions here, fewer up here. Okay, so you have a, oops, there we go, a rectangle to label to illustrate the pH scale. Okay, So on your pH scale, we're going to label the scale 0 to 14. In the middle, you have 7. Oops. So you need to put a dotted line down the middle. We're going to label this box the concentration of hydrogen ions, and this box is the concentration of hydroxyl ions. So as the box for hydroxide is going to get bigger as we get closer to 14, it increases the number or quantity of hydroxide. At 11, or not 11, at 7, the hydrogen ion concentration is going to equal the hydroxide concentration. Oops. So as the box or as the triangle gets bigger or gets smaller for hydrogen ions, you have the most hydrogen ions here. You have the least hydrogen ions here. So you need to label that. You can also add, although it's not always going to be part of the definition, the closer to 7, the weaker something is with regard to acids and bases. So the weak acids are close to 7, and you can put the individual 8, 9, 10, 11, 12, 13, 14. The strong acids are farther away from 7. The weak bases are close to 7. The strong bases are farther away from 7. Now, you'll also see the term alkaline, and that is the same as a base. So if we put the pH scale back, you can see the placement of blood. You can see the placement of bile. It's on the base side. Household bleach, milk of magnesia, household ammonium, oven cleaner, and lye way out here. You have cow's milk. You have saliva. You have the big range for urine, black coffee, tomatoes, soft drinks, citrus juices, vinegar, gastric juice, a 1 molar solution of hydrochloric acid. All right, comparing acids and bases. Again, there's multiple ways that you can define these terms, and these are only some of them. So in the table that you have to compare, pH values for acids is less than 7. Oops. Sorry. It contains large amounts of hydrogen ions It releases hydrogen ions in solution. A hydrogen ion is basically a proton. So we call it a proton donator. Examples: hydrochloric acid, a full quantity, 1 molar solution. Gastric juice also contains hydrochloric acid. Carbonic acid is going to be more up here in the weak acids. H2CO3, amino acids, and fatty acids. So they have organic acids as well. Bases, pH values of less than 7, small amounts of hydrogen ions. They release hydroxide ions in solution, and so they're a proton acceptor. They will bond or bind to hydrogen ions. Example, you have sodium hydroxide, sodium bicarbonate or bicarbonate of sodium, ammonia, NH3. You can see household ammonia that we use to clean, milk of magnesia, an antacid, household bleach, bile, and blood is on the weak base side. Okay. Buffers are mechanisms to regulate pH levels. Usually we use weak acids and weak bases to cause small changes in the pH levels because we don't want big changes, we want small changes. There are two kinds or two types of buffer systems. You have chemical buffers and they react quickly, so within a few seconds, but they only react on a local or small area, small volume. We use compounds and ions found in bodily fluids to carry out chemical reactions to help maintain pH levels. Chemical buffer systems. We also have physiological buffers. They take longer to respond, several minutes to several hours, but they have a bigger impact on pH. The respiratory and urinary systems are going to act and provide a mechanism to alter pH levels. And that's why those two systems are put with this chapter, because they regulate pH levels and they regulate fluid levels. Okay, so chemical buffers. 3 examples is what we're going to go over. Bicarbonate ions and carbonic acid buffers are going to use carbon dioxide and water, which we have lots of in blood and other bodily fluids. If we need more acids, we're going to make carbonic acid. If we need more bases, we make bicarbonate. This is our main extracellular chemical buffer. And you have this already written in your notes. It shows the combining of carbon dioxide and water to form carbonic acid. Notice the arrows go both ways, so the reaction can go either way. Carbonic acid can be dissociated into bicarbonate ions and hydrogen ions. You also need to know the ratio, and that's what we see down here on this balance. There's 1 carbonic acid molecule to 20 bicarbonate ions. 1 carbonic acid to 2, it's a ratio, or to 20 bicarbonate ions. HCO3 with a negative charge. Don't forget the negative charge. So that's where we keep the blood pH in that 7.35 to 7.45 range, which is a very narrow range to keep pH in. So that's why we're going to use 2 chemicals that we have lots of in the blood. This is why most of the carbon dioxide is converted into bicarbonate ions in blood. Remember, that was the 70% of carbon dioxide in the blood gets converted into bicarbonate. It's our main chemical buffer, especially in extracellular fluid like blood. Okay, the second chemical buffer are the phosphates. It's mostly intracellular. Phosphates can act both as an acid and a base. And so if we go this direction and donate hydrogen ions into solution, it acts as a base. If it goes back this way and it bonds to hydrogen ions, then it's a base and we form bicarbonate with a negative charge, or not bicarbonate, phosphate with a negative charge rather than a 2 negative charge. Okay. Proteins are found both intra and extracellular spaces, so they act as both intra and extracellular buffers. The carboxyl group can donate hydrogen ions in solution. It's an organic acid. The amino group can bind to hydrogen ions, forming an ammonia ion. So it can act as a base in that instance. All right. So this ammonia base does not release hydroxide ions in solution. So again, those traits of acids and bases, they may not both fit. So those are your 3 main chemical buffers. Okay. Physiological buffers. The respiratory system responds in 1 to 3 minutes. You can breathe more quickly to get rid of more carbon dioxide, or you can breathe slower, and that's going to hold on to carbon dioxide. Again, we typically equate your concentration of carbon dioxide to your hydrogen ion concentration. So if you're getting rid of more carbon dioxide, you're getting rid of acids. If you're holding on to it, then you're increasing acids in the body. Urinary system, it's going to take longer, a few hours. You can add acids and bases into urine to get rid of them. Urinary system is also a detoxifier. So the kidneys also detoxify substances. So that way you can make them more acidic or more basic and dump them into urine. Both systems can compensate for each other. So we talk about urinary compensation and respiratory compensation. If the respiratory system can't compensate quickly enough, then the urinary system has to take over. If the urinary system can't compensate, then the respiratory system can't. It will take over. All right. Too many acids and too many bases. Acidosis is got symptoms. Blood pH ranges from 6.8 to 7.35. This is going to cause a depression of the central nervous system. So you're going to see disorientation. You can see seizures, loss of consciousness, and coma. One type of acidosis is called ketoacidosis, and there's also the fruity or acetone smell to the breath and urine. So, what happens if we go below this 6.8? We can't compensate for that. We can't fix it. So death is going to occur. Again, this is in the blood pH. Yes, your stomach has a pH of about 2. Okay. So, causes of acidosis. We typically have them divided into metabolic causes and respiratory causes. Metabolic causes. Starvation. When you starve yourself, your body starts breaking down ketones, and that goes back to that ketoacidosis. And so ketones are going to act as a poison and increases the hydrogen ion concentration. Chronic diarrhea can also lead to too many acids in the body. Hyperkalemia, that's too much potassium ions, can cause acidosis. Excessive consumption of alcohol, aspirin, or laxatives. Okay, breaking this down. Too much alcohol, when you break it down, it generates acids. Aspirin is an acid. When Bayer came up with aspirin, it caused stomach upset, which is why you tend to have to take that, and ibuprofen with food. The next company came along, and that's where Bufferin came in. Bufferin added a buffer to the aspirin. Too many laxatives goes back to chronic diarrhea. Excessive flushing of materials out of your digestive tract can increase the acids in the body. Respiratory causes. Anytime you have impaired gas exchange, like pneumonia, you're not going to be breathing as much with pneumonia because you've got fluid in your alveoli. Tuberculosis, an infection that can settle in the lungs or other organs. In the lungs, it's going to create scar tissue in the alveoli, so it prevents gas exchange. Asthma, reduced airflow, impairs gas exchange. And then you have a whole cluster of chronic obstructive pulmonary disorders. 2 of them are emphysema and chronic bronchitis. Emphysema is kind of like osteoporosis. In osteoporosis, you lose bone tissue. In emphysema, that's where you see the individual alveoli, and rather than having lots of surface area, you have less surface area. so less gas exchange. Chronic bronchitis, again, narrowing of the bronchi impairs gas exchange. Okay. On the other end of the spectrum, you have alkalosis. Alkalosis is when you have a pH of 7.45 up to about 8.0. This time, the symptoms include overexcitation of the central nervous system. So you're going to see agitation, irritability, increased muscle activity, tremors, shaking, muscle spasms, and that can lead to convulsions. We also divide the causes into respiratory and metabolic. Metabolic causes include overconsumption of antacids, persistent vomiting, and hypokalemia. So, drinking a bottle of Maalox, eating a box of baking soda is not good for you. Persistent vomiting, getting rid of your stomach acids in large volumes, reduces the pH or increases the pH, reduces the hydrogen ion concentration. So low potassium levels can cause alkalosis. Respiratory causes, an anxiety attack or hyperventilation. Increasing your respiratory rate is going to, like in an anxiety attack, when you breathe really, really fast, you're blowing off carbon dioxide. You're getting rid of too much. Hyperventilation. They used to tell you to breathe into a paper bag. Well, in this case, plastic is not an option instead of paper. So you need to sit down and bend over. And that limits the amount of space that your diaphragm has to work. Again, if we go beyond the 8.0, we can't fix it. Death is going to occur. Okay. One other thing about acidosis, going back to this overconsumption of alcohol. There used to be a lot of deaths in drunk tanks because being overconsumed alcohol mimics loss of consciousness, disorientation, mimics alcohol intoxication. And so several people died because they didn't know the difference between the signs of acidosis and alcohol intoxication. So you got to pay attention. So that's the end of chapter 24 over fluid, electrolyte, and pH balance. Again, you have these recordings. You don't have to just look at them once to get your notes. Oops.